Alrighty, welcome to physics. Here we will be looking at series circuit practice 1, and probably just part 1. So let's get started. So the main rule we'll be using here is Ohm's law that tells us the relationship between the change in voltage or the potential difference across the resistor is related to the current going through that resistor and its resistance. All right, and then we also have our two ideas of conservation of charge, which tells us in a series circuit like this, one loop, the current, the charge per second going through each spot in the loop is the same. And conservation of energy, which says that the change in energy here, or the change in potential when we're talking about energy per charge, across one entire go around has to be 0. So whatever energy potential I gain, electric potential I gain by the battery, I lose across the resistor. We'll see later that that ends up also conserving energy in terms of power is really the reason why energy is conserved here. All right, determine the voltage drop across the resistor. So I've got this battery, it's 100 volts, so if I'm dealing with perfect wires, which we are, this whole section has 100 volts more, 100 more joules per coulomb than this section. It doesn't change across these perfect wires, so I know if I'm gaining 100 here, well, going from red to yellow, here I'm going from yellow back to red, I need to lose 100. So across this resistor here, I know its change in voltage has to be 100 volts. All right, so let's say 100 volts. The current through the resistor. Well, I know the resistance of the resistor, 20 ohms. It's changing the voltage by 100 volts. I can use Ohm's law, delta V equals IR, to figure out what this current needs to be. I has to be 5 amps going through here. 5 amps. Current running through the battery. Well, conservation of charge tells me one loop, 5 amps going here, 5 coulombs every second are also going through the battery. Circuit with two resistors in series is shown. Determine the equivalent resistance of the circuit. So equivalent resistance, that's when I can treat the circuit as just being a simple circuit with one resistor. And I know in a series circuit, due to conservation of charge and energy, I can just add these two resistors to get the equivalent resistance of 20 ohms, 15 plus 5. From there, it's easy to use that to find the current. If I have 100 volts, that means the resistor has to lose 100 volts. So it's changing it. 100 volts equals I times 20 ohms. So current 5 amps. You'll notice that our equivalent resistor for this question is the same as our actual for the previous question. Totally on purpose. Determine the potential difference to change voltage across each resistor. All right, color code this just for practice. This has the same resistance. This has not resistance, voltage. All right, so these are equal potential places. This is at the same height, I could say. This is at a different height, and this is at the lowest height, right before the negative terminal there. This has 100. If I call this 0, all right, my first resistor here, how much does it change it by? Delta V equals IR. I found the current was 5 amps. So 5 amps, 15 ohms. And the reason that the current is the same here as it was in my equivalent one is because, again, I just had one loop either way. Same loop. Is 75 volts. So just for practice, that means 100 volts losing 75. I could say this has a potential in this area of 75 volts. If I've said this is 0. 0 gains 100, loses 75. Oops, that should be 25. Can't do math. 25 volts. All right, so how much does this one change it by? Well, I could look and I could say, well, this is 0, this is 25, so the change in voltage here has to be 25 volts. Right, technically, these are all negative changes in voltage. We're just doing magnitudes. I could also do that by saying 5 amps times 5 ohms also gets me 25 volts. So do it both ways, should get the same answer either way. Checks our work. Series circuit. Batteries outputting a current of 5 amps. Determine the potential difference across each resistor and the potential difference across the battery. Let's first do it with equivalence resistance. We pretend I just have this. This would be 13 plus 8 plus 9. It's 30 ohms. The current I can say is 5 amps because it's a single loop. Same everywhere in the loop. So it's the same on my equivalent circuit. So that means overall this resistor has to be changing it by whatever the battery has. So this resistor is changing it, delta V IR. Five amps, 30 ohms, 150 volts. So again, if I say this has 1 voltage, this has another voltage, and I say this is my 0, right before the negative terminal of the battery. Well, this took away 150, so this is 0. This had to have been 150 volts because it changed it by 150. All right, well, that means the battery's taking it from 0, it's bringing it up to 150. The battery has to have a potential difference of 150. So we just kind of skipped ahead to B there. Let's go back and do A, potential difference across each resistor. And that will confirm what we just did it the other way. Again, I can color code areas of equal potential. Just to practice that. So I have 4 different potentials in this question. Yeah, I'm going to say before the battery, I'm going to choose that to be 0 volts. Delta V equals IR. Ohm's law. We're told the current everywhere, 1 loop, 5 amps. So 5 times 9, 45 volts. 5 times 8 is 40 volts. 5 times, that's a 13, I think, is 65 volts. All right, and we can check that that works out. Overall, we have a change of 45 plus 40 plus 65, so that's 150, which is what we got for B. Might as well look at what our different voltages are. I'm going to go backwards here. So I don't know what the battery is doing. I can't really figure this out, but I can say, oh, this is 0. And this changed it by 65, so my purple area has to be 65 volts. And I had 65. I changed it by 40, I took away, so this had to be 105 volts. Because when I went across it, I lost 40. All right, here it's 45, so 150 volts. Great, which means the battery's taken from 0 to 150, the battery needs to be doing 150. Series circuit is shown below. Determine the resistance necessary for R2. Current of 2 amps to flow through the circuit. 2 amps. Determine the potential difference across each resistor. Let's do some color coding. I always like using red for the 0 potential. Green for right after the battery. So again, I'm going to arbitrarily say this is 0. It's my 0 point. And because I know the battery is 150, I know this then has a potential 150 along this perfect wire. I look at this resistor here. It's got 50 ohms. It's got a current of 2 amps going through it. So that's V equals IR, 100 volt change. 100 volt change. I've got 0. So this had to have been 100. Here's 100, changed by 100, 0. So I can find that the delta V across this resistor has to be 50. Because I have 150, I'm dropping to 100. 50 volts. Well, I have a current of 2 amps, a delta V of 50. So I know the resistance R has to be 50 over 2, 25 ohms. Right. Now we could cheat and do this. No, and by doing it this way, we've actually answered B already. But we could have done the equivalent resistance method. We could have said this is 150 volts. This is our equivalent resistance, current of 2 amps. Again, 2 amps is a lot of current. I can say here, this resistor is taking it from 150 to 0, changing it by 150, exactly what the battery is doing. So our equivalent of delta V equals IR. Our equivalent is then 150 divided by 2 amps is 75 ohms. Right. And then this is 50. I know in series I add them. 50 plus what is 75? R2 has to be 75 ohms minus 50 ohms equals 25 ohms. right? And then again, to get B, I just say, okay, 25 ohms times 2 amps is 50. And then 2 amps times 50 is 100. So meanwhile, you add more light bulbs in a series circuit, the lights get dimmer every time. Well, the potential difference is not changing, right? If I just have a light bulb and I'm keeping the battery or whatever my potential source the same, as I add light bulbs, I'm adding resistors. Or bulbs gives me more overall resistance. Because we saw when I have in series, I just add their resistances. Mm-hmm. And I'm going to specify here a series circuit. We'll find that this is not the case for a parallel circuit. If I have more resistance, I'm going to get less current. Which means if I look at the voltage drop across each bulb, well, each bulb now has less current, so it does not take away as much energy. So it's not going to be as bright. We could also talk about power when we get to power next time. Less current is going to mean less power, which means less brightness. All right, each bulb in a string of lights has, this is 10 ohms. Maximum current it can handle is 0.1 amps. The maximum number of bulbs needed in a string. All right, if I don't have enough bulbs, right, we just talked about more bulbs gives me less current. That means if there's not enough bulbs, I'll get too much current, which would make them explode. So we have a standard 110 volt battery, and we're just adding resistors until we have enough. Okay, so one way to think about this is I know I want a current of 0.1 amps. So I can figure out what overall resistance I need, right? I can pretend I have a equivalent resistance. And that would have to be 110 volts equals 0.1 amps times equivalent. I get the equivalent has to be 1,100 ohms. So how many light bulbs would I need to get that? Well, I know in series I can add them, so it's 10 ohms times my number of bulbs has to be 1,100 ohms. God, my ohms are terrible. So that means my number of bulbs has to be 110. I can have 110 light bulbs strung in this Christmas light chain in order to make it so my bulbs are okay. Really, I would want more than that because I probably don't want to be at the maximum current the bulbs can handle. All right. Cool. Another way to do this is 110 volts. You can say, well, in the series circuit, if they're all the same resistance, they're all going to have the same change in voltage. 10 ohm resistor with 0.1 amps, V equals IR. 10 times 0.1 is 1 volt, so each bulb is going to be changing it by 1. So to get rid of this whole 110, I need to change it by 110 times. So I need that many bulbs. All right. Power, we'll do that later. Peace.